You know, the James Webb Space Telescope has just thrown us a massive cosmic curveball, a discovery so strange it might force us to rewrite the entire story of how our universe grew up.
So let's just start with this question right here. It kind of flips one of the most popular ideas on its head, and it really sets the stage for the pretty radical solution we're about to dive into.
All right, so where does all this craziness begin? Well, it starts with an absolutely startling discovery from the James Webb Space Telescope, one that seems to break our best models of the cosmos and has astronomers everywhere scratching their heads. To put it simply, Webb peered back to the very dawn of time and found galaxies that are, well, they're absolute behemoths. The problem is, they showed up shockingly early to the cosmic party, long before we thought such giants could ever exist.
I mean, we're talking about structures with the mass of 10 billion suns. 10 billion. And they were already there, fully formed, when the universe was just a baby, only about 600 million years old. That's like finding a newborn that already has the body of a full-grown adult. It just doesn't make sense.
And this is a huge problem. For cosmology, it's a full-blown crisis. It's not just that these galaxies are big, it's that according to our best theory of the universe, they simply shouldn't be there at all. You see, our rulebook for the universe is something called the Lambda CDM model, and it's been incredibly successful. It explains how gravity, slowly, over billions of years, gathers up gas and dark matter to build galaxies. Think of it as setting a kind of cosmic speed limit on how fast the galaxy can possibly grow. This chart just lays the problem out perfectly. The blue bar, that's the absolute max size a galaxy is supposed to be at that early time, according to the rules. But the red bar? That's what Webb actually found. And it's not a small difference. The observations completely shatter that theoretical speed limit.
In fact, to try and force these galaxies into our existing model, you'd have to assume something called a star formation efficiency of over 100%. Basically, you'd have to convert more than all of the available matter you have into stars. It's not just unlikely, it's physically impossible.
Okay, so we've got a clear contradiction. What we see doesn't match our theory. To find a way out, some scientists are looking back to a really strange cosmic coincidence that has puzzled physicists for decades.
For decades, scientists have noticed this bizarre numerical connection. It links the expansion rate of our universe with this tiny, fundamental acceleration scale called A0. Now, A0 is sort of a minimum threshold for gravity's influence. But nobody knew why these two completely different numbers lined up so well. Was it just a fluke? But a new theory says no, it is not a coincidence. In fact, it predicts the ratio between these two numbers should be 0.184. And the observed value? It's 0.183. I mean, that is an astonishingly close match. It suggests they're deeply connected, like two sides of the same cosmic coin.
And this brings us to the really radical new idea proposed to solve all this. It's called mode identity theory, and it suggests that one of the numbers we've always assumed is a fundamental, unchanging constant of nature actually changes.
Okay, this is the core idea, so lean in. For 40 years, we've just assumed that this acceleration scale, A0, has had the same exact value for all 13.8 billion years of cosmic history. This new theory says the exact opposite. A0 isn't fixed at all. It actually changes over time, linked directly to how fast the universe is expanding.
So how does this one simple change fix the whole mystery? I mean, if A0 is different in the past, how does that help us build these impossible galaxies? Let's connect the dots.
Okay, so let's go back in time to that early era about 600 million years after the Big Bang. In cosmology, this is called redshift 10. You can just think of it as a cosmic timestamp. The key thing to know is that back then, the universe was a lot smaller, and it was expanding much faster than it is today.
And here is where it all clicks together. First, that faster expansion means A0 was also stronger, about 20 times stronger. That stronger A0, in turn, basically supercharged the force of gravity, which allowed galaxies to form on hyperspeed.
So how much stronger are we talking? Well, the math works out to a boost of about 4.5 times the effective pull of gravity. And trust me, in the early universe, that is a massive difference.
Think of it like this. In the early universe, gravity's volume knob was cranked all the way up to 11. This supercharged gravity allowed all that gas and dark matter to collapse into galaxies about twice as fast as our old models predicted. And just like that, those impossible galaxies become entirely possible.
But look, this is more than just a convenient story.
A good scientific theory has to make testable predictions. Otherwise, it's just not science. And this new theory makes some very clear, very bold predictions that we can actually check.
What's so cool is that this theory completely flips the standard script. It predicts that A0 evolves, but at the same time it suggests that the cosmological constant lambda, that's the force driving the universe's accelerated expansion, it remains fixed. And that's the exact opposite of what many other alternative theories assume.
This gives us a clear mission. We can point our telescopes at distant galaxies and actually measure A0 back in time. The theory predicts that at redshift 2, it should be about 3 times stronger than it is today. If we make our measurements and find out it hasn't changed, well, then the theory is wrong. Simple as that.
So what's the big takeaway from all of this? I think it might just be this powerful, almost poetic idea. The impossible galaxies weren't impossible at all. They weren't formed in an older universe, but in a stronger one, where the fundamental forces allowed them to grow up faster than we ever imagined. It really makes you wonder, what else is hiding out there in the cosmic dawn, just waiting to change everything we think we know?